Everyone, you're welcome. This is Shadows Academy. You're welcome to my channel. It's a channel for maths and physics. So please click on the link below. Like and subscribe. Please like and subscribe. Thank you so much. Shadows Academy. You're welcome. This is Shadows Academy. Today we are going to be looking at the Laplace Transform. Now the Laplace Transform is actually one of the many integral transforms in mathematics. We have certain integral transform in mathematics. We have the Fourier transform, the Henkel transform, and few others. And the Laplace transform is one of them, and a very useful transform. Basically, as you can see here, the Laplace transform helps us to convert real variable to a function of complex what? Variable. So when you're taking a function of real variable into the Laplace transform, it is going to transform it to a function of complex variable. And of course, the Laplace transform is widely used in solving differential equation. And one of the reasons why the Laplace transform is so good in solving differential equation is that if you take a Laplace transform of a particular differential equation, it will automatically convert the differential equation to a statement in algebra, and it is easier to proceed and deal with algebraic expression compared to a differential equation. So that is one of the power of the utilization of the Laplace transform as a mathematical tool. And as we have here, this is the representation. The Laplace transform is simply an integral, and as we earlier said, it's an integral transform. This ft is our function in real variable t, and then fx is our complex function in complex variable s, as we have here, is a complex number which is defined as this. So this is the representation of our Laplace transform. In a more concise form, we can use this as the representation that fx is simply the Laplace transform of ft. Okay, so we are quickly going to take a particular example to understand how to make use of the Laplace transform integral. So the question is, determine the Laplace transform of the function cos at. So what we have here is our real variable function cos of at, and we want to actually find the Laplace transform of this. Remember that our Laplace transform for fx is defined as the integral from 0 to infinity of ft exponential minus st dt. This is our Laplace transform. So we make a substitution. F of x is our integral. F of t is cos of at exponential minus st dt. So to find the Laplace transform of the function f of t is equal to cos at actually means to solve this particular integral. So what do we have here? We have an integral of a trig function cos at and an exponential function exponential minus st. So one of the quickest and easiest approach is to rewrite this trig function in an exponential way, so that everything will just be an exponential integral. So say since cos 80 can be written as exponential 80 plus exponential minus I80 and exponential I80 over 2. So this is a way to express our cos 80. So we are going to make a substitution of this into this. Let's call this equation 1. So we substitute into equation 1. And when we do that, we have f of x is this. We have our exponential I80 plus exponential minus I80 over 2. Then we have exponential minus st dt. So we can split this to have two different integrals, which is 1 over 2 of this dt plus 1 over 2 of this. So what we did was to use this exponential that is outside the bracket to multiply each of these what? Term. And remember, over 2 simply means you can make both, you can divide them individually by what? By 2. And remember, in integration, we have the liberty to take 1 over 2 to the back of the integral because it's simply a constant. So what we now do is to find the solution to this integral and the solution to this integral. But then, look at this. What are you seeing? This is actually a particular Laplace transform. And this is also a particular Laplace transform. So what we are going to do is to make use of that particular Laplace transform of this and substitute into this expression. So let's call this equation 2. So we are going to make use of the Laplace transform of this. So the Laplace transform of exponential I80 is definitely 1 over x minus IA, while the Laplace transform of exponential minus I80 is 1 over x plus IA. So what I'm going to do is to make a substitution of this, replacing this with this result, and I will also replace this with this particular result. So when I do that, I'll say substitute into equation 2. So I have my f of x is 1 over 2 a2 bracket 1 over x minus ia. Then I have plus 1 over 2 a2 bracket 1 over x plus ia. So I've made a substitution of the individual Laplace transform. So the final thing to do is to simplify this by the rules of algebra. So we are going to end everything by quickly simplifying that expression. So we have f of x is, I can factor out 1 over 2 and take the denominator of x minus ia and LCM of this. When I add the two fractions, this goes in this, you have this x plus ia plus this goes in this, you have this x minus ia. So we have our f of x is 1 over 2 this cancels this. You have 2x over, when you open up this bracket, you have x, both are same expression but of different signs. So we can just multiply s times s to be s squared. IA times IA. Remember, this is a complex identity, the I. So I times I here is the I squared, which is the same thing as minus 1. So you have it, the minus multiplied by this minus, you have it as plus a squared. With a small note that I times I is I squared, which is minus 1. So these two cancels these two. Our Laplace transform becomes x over s squared plus a squared. So what is the conclusion? The conclusion is that the Laplace transform of cos of at is the same thing as s over s squared plus a squared. So this is our Laplace function in the complex variable x.